Good day, dear colleagues. We invite your attention to a report on the topic segmentation of analog matter readings using neural networks. As you know, one of the constraints to the implementation of the concepts of smart home, smart city, industry 4.0, agriculture 4.0, etc., is the need to integrate analog energy metering, for example, water, gas, and electricity meters. Often the replacement with digital devices is not cost-effective. This may be due to the ban of making change to communications, the high cost of development, design and technical documentation, a large number of analog accounting tools at the enterprise, etc. One option to overcome this barrier could be a combination of artificial intelligence and Internet of Things technologies. At the same time, an optical channel for digitizing readings based on the recognition operation is very often used to transform analog matters into digital ones. However, we have significant drawbacks that affect mass adoption. Here it is necessary to indicate high requirements for the spatial stability of image and exposure parameters, the lack of unification by types of counters and fonts, and the influence of vibrations with certain specifics of technological production processes. In addition, the user-age computing has to adjust to limited computing resources, low-resolution images, typically around 28 by 28, the need for manual segmentation, accurate initial setup, and manual correction of reading data. One of the options for solving this problem can be use of an image segmentation procedure before recognition. The technical implementation of this approach is possible due to fork computing technologies. The aim of the work is comparative analysis of the accuracy of possible options for solving the problem of semantic segmentation of images of digital displays of counters based of neural networks. Using this architecture of the so-called large PSP, we will consider this approach as a starting point for research. It should be noted that the choice of one or another format of the recompressed image, in addition to the maximum possibility of maintaining of proportions of the original image of the database, should also take into account the existing limitation of the computing resources on which the neural networks are trained. To maximize these resources, the study used the graphical mapping capabilities of Google's Globe Pro Plus Surf in Learning. The learning process of the PSP neural network was performed with a learning step of 0.001 and batch 16. The installation of batch 32 was accompanied by an insufficient resource error. The learning dataset contained 870 images, and the validation dataset contained 374 images. The masks used for image segmentation were black and white. The percentage of space occupied by the black background was 90–80%, while the white cathode for digital display counted for 2%. The runtime for 200 learning epochs is standard Google Globe Pro Plus connection mode with V100 graphics card equipped with 16 GB of RAM was 32 minutes. Next, we explored the option of modifying the original PSP architecture by replacing the conv2D transpose layers with upsyncing and max pooling with average pooling. Even greater improvements in accuracy were achieved by using a modification of the PSP network, which consisted in increasing the number of convolution layers with the ReLU activation function in each of the channels up to 8. The size of the cores remained the same 3 by 3, fixed for all 4 channels. Pooling branches also remained, and the number of convolution kernels is 60. In this case, both normalization layers were used in each channel, and additionally a droplet layer with a data thinking factor of 0.1 was applied at the channel output. This structure has been given the conventional name PSP Block 2D. As a result of learning for 116 epochs, the accuracy of the class with the worst segmentation quality on the test sample reached 73%, and the average class accuracy reached 86.2%. In left figure illustrates the learning process described, and right figure the segmentation quality on the validation set. At the next stage, the studies were carried out using a neural network of the UNet type. This figure shows the architecture of the light version of UNet. The relative simplicity of its architecture made it possible to switch to the original 432 by 240 pixel dataset and easily carry out long-term learning for 6 to 2 epochs with a batch of 60 and final learning step of 0.0001. The calculation time of one epoch fluctuated within 27-28 seconds. Already at the 5-fourths epoch, an accuracy of 88.4% was achieved, and then it took more than 400 epochs for the maximum achieved accuracy to stabilize at the level of 88.8% at the 4/6-fourths epoch. Not only the architecture for the neural network contributed to the improvement in accuracy, but also the larger image format during learning. Further complication of the architecture was carried out by switching to a neural network of the UNet++ type. In the course of computational experiments, it was found that with neural network work with BAT4, but not as efficiently as a large and medium UNet. As you might expect, BAT8 at 0.001 gives better accuracy than BAT4. Also, UNet++ works on BAT60, but much worse at 0.001. The resulting accuracy for different BAT sizes is presented in table. The so-called UNet was considered as a maximum complexity of the neural network architecture. In this case, a 240 by 432 pixel image dataset made it possible to work with batch 4, 8, and 60. The maximum accuracy with BAT60 and a learning step of 0.001 was 86% at the 8th epoch, and with BAT8 it was 88.5% at the same epoch 18. Thus, the UNet neural network demonstrated more intensive learning. On this slide is presented a comparison of the architectures of all considered neural networks. As you can see, a larger architecture doesn't necessarily give a better result. The hardware implementation can be based on the Raspberry Pi Zero processor board, the neural network on the ESP RE2, Alternatively, you can use the ESP32CEM module, which is currently the most cost-effective option for implementing edge IoT. Given the relevance of edge computing, it is advisable to explore the possibility of implementing segmentation and recognition based on TensorFlow Lite on devices such as ESP32CAM. The approach considered in the paper can be used not only in the interest of creating digital infrastructure. A promising direction is the development of uncrewed platforms that use vehicles initially oriented towards human control. At the same time, to read the indicators of the sensor, for example, a speedometer, engine speed, oil pressure, etc., video cameras with neural networks can be used similar to the options discussed here for household matters. The authors plan to continue further research on the possibility of using neural networks based on the use of object detection technology with making digital displays using bounding boxes using the results. This is the concluding of my briefing. Thank you for your attention.